Good morning, we seem to be live. Go ahead and share out our status and get the day started. Looking at the preview, it looks like there's a little tiny bit of static around me, but it's not as bad as it used to be. But all my lights are on, so I'm not exactly sure what the best solution to that is. Get this out to Slack. And to Twitch or Twitter. All right, and done. Okay, so hopefully chat is working just fine. Our preview is working. It's so interesting. It's so very dark here, but my preview over here isn't that bad. I'll just pause that for a second, and let's figure out where we're at. So currently at sending multiple values and seeing the receiver waiting. Okay, let's go ahead and open up our terminal and get to our previous code. Okay, so we have channels and threads. This said new. No, it isn't. I think this is channels where we're at, but we'll just keep that there, and then we'll open up code if we need to. Until then, let's continue on. Sending multiple values and seeing the receiver waiting. The code in listing 16.8 compiled and ran, but it didn't clearly show us that two separate threads were talking to each other over the channel. In listing 16.10, we've made some modifications that will prove the code in listing 16.8 is running concurrently. The spawn thread will now send multiple messages and pause for a second between each message. Oh yeah, I remember us doing that. This time, the spawned thread has a vector of strings that we want to send to the main thread. We iterate over them, sending each individually, pausing between each by calling the thread sleep function with a duration value of 1 second. In the main thread, we're not calling the recv function explicitly anymore. Instead, we're treating Rx as an iterator. For each value received, we're printing it. When the value is closed, iteration will end. When running the code in listing 16.10, you should see the following output with a 1 second pause between each line. Because we don't have any code that pauses or delays in the for loop in a main thread, we can tell that the main thread is waiting to receive values from the spawned thread. Creating multiple producers by cloning the transmitter. Earlier we mentioned that MPSC was an acronym for multiple producer, single consumer. Let's put MPSC to use and expand the code in listing 16.10 to create multiple threads that all send values to the same receiver. We can do so by cloning the transmitted half of the channel, as shown in listing 16.11. So we're getting the channel. This is what's interesting. Okay, let tx1. So a second tx, MPSC sender clone at tx. So then we threads. Oh, we're going to do 2 thread spawns, and they both do the same thing. They both send after some time. And the Rx can receive both of them. Okay, so let's go do that. All right, so we have thread spawn. I think for this one, okay, so I need to redo this just a little bit in order to have the same type of message coming out here. Thread spawn move, transaction send, a value, and then unwrap. Oh, I was basically playing around with like sending things from outside and like how that whether or not it moved in, it was available later, and of course it wasn't. So we don't need to send this right now. This is fine, but I think what we really want to do is create ourselves a vector. So let messages equals vec, and to the strings it will be well, probably does it need to be strings? I think they do need to be strings. Are you using strings here? Yeah, string from. String from first second third fourth. Okay, so then we can do the same thing with the other one. Also, you're unhappy because semicolon. Okay, so then we need to send. So tx dot, I think it's send. We're gonna send. Oh, well, we can't just send that on its own. We're gonna have to loop through. So for message in messages dot not that iter. So now I should have the content of like whichever one of these vectors we have, and we can send this. So tx dot send message dot unwrap. Okay. So we send that out. Messages does not live long enough. Borrowed value doesn't. I create messages here. It should. Oh. I'm curious that. I guess it's because the thread might die beforehand. So messages does not live long enough. Borrowed value does not live long enough. Borrowed value must be valid for the static lifetime. Well, so let's go take a look at how they're doing it again. The thread spawn move that vals equals vector for val and vals. Oh, I guess I don't need the dot iter. Can you do for message in? I don't seem to need to do. Can you do for messages and messages? I shouldn't need to though. Let's do what they're doing, which is not use the iter here, but just say for message in messages. Okay, that works a lot better. So I was clearly getting a reference to the message instead of the actual thing. So this is a better way of doing it. So this is the first, and we need a second one. So let tx1 equals MPSC maybe it's MPSC dot. Okay, let's go take a look at what it is again. MPSC sender clone, and then a reference to TX. Okay. Sender. Oh, come on. You're not going to tell me that? Sender clone, okay. And then a reference to TX, and then this will give me a copy, a clone of this. Also, I forgot to say, I have no idea how to pronounce your username. PWR per nonsense. Good morning. Welcome to the stream. Okay, so transaction 1, we've cloned it. Now we can copy you and do the same thing here. Thread spawn move, messages equals this. So we can do another set of messages. We'll send these all, except instead of TX, it'll be TX1. And what do I need to do with this? Nothing new. So duration, I need to set the duration. So for these threads, now we have this loop, which is matching and just basically looping around forever. And I don't know if I need to do that with here. For received and RX. So I don't need to do this either. This was another play around thing I had. So received and RX. Then I just want to print this. So print line. Well, maybe I'll just do the message and received. I need to do like a dot unwrap on it. Oh, apparently not. Okay. I guess it has an iterator by default that works out for me. So if I do this, it won't work out too well for me because probably this spawn works out first, second, third, fourth, and then we'll get another set of messages right afterwards. Let's run that and verify that. So cargo run. Yeah, so because we're not sleeping and having idle processes on the CPU, it's going to run everything it can first on the first thread, and then it's going to run everything on the second thread as it closes that first one down. But when we sleep, so transaction send, we can do thread sleep duration from seconds 1. And I can repeat this down here. So now it should go back and forth between each one sometimes because the CPU will be in sleep mode, and so it's like, well, I don't have anything to do. I might as well go over to another thread and work on it. Nice, so that one was every other one, just sort of how we expected it to be. This time, before we create this first spawn thread, we called clone on the sending end of the channel. This will give us a new sending handle we can pass to the first spawned thread. We pass the original sending end of the channel to a second spawn thread. This gives us 2 threads, each sending different messages to the receiving end of the channel. When you run the code, your output should look something like this. Sort of. You might see the values in another order, or it depends on your system. This is what makes concurrency interesting as well as difficult. If you experiment with thread sleep, giving it various values in the different threads, each one will be more non-deterministic and create different output each time. Now that we've looked at how channels work, let's look at a different method for concurrency. Shared state concurrency. Message passing is a fine way of handling concurrency, but it's not the only one. Consider this part of the slogan from the Go language documentation again. Communicate by sharing memory. What would communicating by shared memory look like? In addition, why would message passing enthusiasts not use it and do the opposite instead? In a way, channels in any programming language are similar to single ownership, because once you transfer a value down a channel, you should no longer use that value. Shared memory concurrency is like multiple ownership. Multiple threads can access the same memory location at the same time. As you saw in Chapter 15, where smart pointers made multiple ownership possible, multiple ownership can add complexity because these different owners need managing. Rust type system and ownership rules greatly assist in getting this management correct. For an example, let's look at mutexes, one of the more common concurrency primitives for shared memory. I wonder, so they mentioned in Chapter 15 that mutexes were a type of smart pointer. So I wonder if that's the same thing, where basically on the stack, we're only going to hold one or two items, which is just a pointer to an area in heap memory. And that's where everything is going to be stored in the thread, because the mutex can sort of keep track of the growing and closing and make sure it doesn't get accessed incorrectly, I think. Mutex is an abbreviation for mutual exclusion, as in a mutex allows only one thread to access some data at a given time. To access the data in a mutex, a thread must first signal that it wants access by asking to acquire the mutex's lock. The lock is a data structure that is part of the mutex that keeps track of who currently has exclusive access to the data. Therefore, the mutex is describing as guarding the data it holds via the locking system. So basically, you could have shared state, but you can't have shared access. It's one at a time. So we're going to have some kind of not a lock file, but a lock place in memory. Mutexes have a reputation for being difficult to use because you have to remember two rules. You must attempt to acquire the lock before using the data. When you're done with the data that the mutex guards, you must unlock the data so other threads can acquire the lock. For a real-world metaphor for our mutex, imagine a panel discussion at a conference with only one microphone. Before a panelist can speak, they have to ask or signal that they want to use the microphone. When they get the microphone, they can talk for as long as they want to, and then hand the microphone to the next panelist who requests to speak. If a panelist forgets to hand the microphone off when they're finished with it, no one else is able to speak. If management of the shared microphone goes wrong, the panel won't work as planned. Management of mutexes can be incredibly tricky to get right, which is why so many people are enthusiastic about channels. However, thanks to Rust type system and ownership rules, you can't get locking and unlocking wrong. Those are strong words for that. I mean, I guess I could see the compiler can catch almost all those stuff, but I bet things can go wrong if it's difficult. The API of Mutex. As an example of how to use a mutex, let's start by using a mutex in a single-threaded context, as shown in listing 1612. So single-threaded context, use standard sync mutex. That m equals mutex new, we hand in the number 5 into it. That num, so m.lock unwrap. So we get the lock number. Interesting. And a reference to dereference num, and we set it equal to 6. Print line m equals, and then m. Okay, that's a little bit interesting that we're setting the lock, but we're not and we just set it to the arbitrary number 6. Okay, so let's do this though. So I'm gonna create a new, cargo new mutex. All right, so what's the first thing we need to bring? We need to bring in mutex in, and that's in standard sync mutex. There is mutex along with everything else. Okay, so once I've brought that in, then let m equals mutex new. So we're gonna create a new mutex and assign it to m. So this is t for type, maybe, or time, probably type. So it's going to figure out that it's going to be, what is this? I32, U32? I can't remember what the default is right this second. Okay, so that gives us an m. Let mute num equals m.locked unwrap, and then we're going to set. Okay, so this is where it gets interesting. In a block on its own, we're going to let mute num equals m.lock unwrap, and then set num. I guess that's this. It's like changing it to 6 here. So in a new block, well, first of all, let's just print line what this is. So print line m is let's see what we got here. So cargo run. M is mutex data 5. Okay, so then if in a block we then say let mute num equals mutex, and I think it was dot lock dot unwrap then we'll dereference num and we'll set it equal to 6. Expected value found struct mutex. I think it's just m.lock, right? Okay, perfect. So let's run this, and we should get, my guess is 6 for the data. Yeah, exactly. As with many types, we create a mutex t using the associated function new. To access the data inside the mutex, we use the lock method to acquire the lock. This call will block the current thread, so it can't do any work until it's our turn to have the lock. The call to lock would fail if another thread holding the lock panicked. In that case, no one would ever be able to get the lock, so we've chosen to unwrap and have this thread panic if we're in that situation. After we've acquired the lock, we can treat the return value, named num in this case, as a mutable reference to the data inside. The type system ensures that we acquire a lock before using the value in M, mutex I32. It's not an I32. The type system ensures that we acquire a lock before using the value. Oh, okay. Before the value isn't an I32. So we must acquire the lock to be able to use the I32 value. We can't forget the type system won't let us access the inner I32 otherwise. As you might suspect, mutex t is a smart pointer. More accurately, the call to lock returns a smart pointer called mutex guard. This smart pointer implements deref. To point at our inner data, the smart pointer also has a drop implementation that releases the lock automatically when a mutex guard goes out of scope, which happens at the end of the inner scope in listing 1612. As a result, we don't risk forgetting to release the lock and blocking the mutex from being used by other threads because the lock release happens automatically. After dropping the lock, we can print the mutex value and see that we were able to change the inner I32 to 6. Sharing a mutex t between multiple threads. Now let's try to share a value between multiple threads using mutex t. We'll spin up 10 threads and have them each increment a counter value by 1. So the counter goes from 0 to 10. Note that the next few examples will have compiler errors, and we'll use those errors to learn more about using Mutex and how Rust helps us to use it correctly. Listing 1613 has our starting example. All right, so using standard thread, let counter equals mutex new and set it to 0. Let mute handles equals vector. So I'm guessing our threads are going to go into the handle. 4 underscore and 0 to 10, I guess because we're not using it. Let handle equals thread spawn, and then our closure function is going to move whatever's in here. Let mute num equals counter lock unwrap, and then we increment the 1 by 1. Handles.push the handle. Then at the end, for handle and handles, handle.join unwrap. So we're joining them together. I'm not sure how this is working for us. Because they're not numbers or anything. They're actual threads. And printline result, counter lock unwrap, figure out what it is. Okay, so let's sort of begin doing this. I'm gonna try not having to join and see what happens. So we'll do like the bare minimum of this to begin with. So standard sync mutex and standard thread to bring in. So use standard thread. Okay, so we have a let m mutex new 0, and we're going to call this counter. Then we need a thread, so let counting threads equals, it's going to be vec new, so just absolutely nothing in it. Of course, it's going to complain right away that it doesn't know what to store, right? Or not at all. Okay, never mind. We don't need you right now. Say we don't need you either. So now we want to loop through and create a bunch of threads. So for in 0.10. Okay, so for this, we want to create a new thread and stuff it into counting threads. So let thread equals thread spawn, and then we're going to have our, we want to move into here, because we're going to move in the counter, aren't we? And so inside of this closure, we want to get we have the thread. We're going to push the thread in afterwards. It's this counter we need here. So let's c equals counter dot lock unwrap. Then we want a reference to c plus equals to 1. Okay, so that's spawning the thread. We now need to throw something into the vector so it knows what we're putting in. So it's going to be counting threads dot push, and it's going to be the thread t. Okay, what else did we have here? So I think that's everything so far, and then I was going to skip the handle and handles to join. We just want to print line the results from counter.lock unwrap. So print line, the total number is, it's going to be counter dot lock unwrap. I want to dereference it, and a semicolon to end. Let's see what these error messages really are. Cannot borrow immutable local variable counting threads as mutable. So cannot borrow local variable counting threads as mutable. Oh, so we need to make that, yeah, they did it as mutable and I just forgot to. So this needs to be a mute. That should fix the first problem. Capture a moved value counter. So let's see equals counter.lock.unwrap. Value captured here after move. Ooh, interesting. Okay, so the counter itself, which is the mutex, is no longer available afterwards. So move occurs because counter is type standard sync mutex, which does not implement the copy trait. So it couldn't copy the mutex over either. So I'm sure that's one of the big problems that we're going to run into here. We create a counter variable to hold an I32 inside a mutex t, as we did in listing 1612. Next, we create 10 threads by iterating over a range of numbers. We use thread spawn and give all the threads the same closure. One that moves the counter into the thread acquires a lock on the mutex t by calling the lock method, and then adds 1 to the value in the mutex. When a thread finishes running its closure, num will go out of scope and release the lock so another thread can acquire it. In the main thread, we collect all the join handles. Then, as we did in listing 16.2, we call join on each handle collect all the join handles. Then, as we did in listing 16.2, we call join on each handle to make sure all the threads finish. At that point, the main thread will acquire the lock and print the result of this program. We hinted that this example wouldn't compile. Let's find out why. So that's because we moved the counter in. So we are going to have to do this handled handles, but I want to wait until the error message. The error message states that the counter value is moved into the closure and then captured when we call lock. That description sounds like what we wanted, but it's not allowed. Let's figure this out by simplifying the program. Instead of making 10 threads in a for loop, let's just make 2 threads without a loop and see what happens. Replace the first for loop in listing 1613, this code instead. Well, I don't think we necessarily need to do that because we know what's going on. It's this counter here got moved inside of this closure. Therefore, it's not available for anything else, either this closure itself or down here. Down here. We make 2 threads and change the variable names used with the second thread to handle2 and num2. When we run the code this time, compiling gives us the following. So it's the exact same problem. Aha, the first error message indicates that counter is moved into the closure for the thread associated with handle. That move is preventing us from capturing counter. When we try to call lock on it and store the result in num2 in a second thread. So Rust is telling us we can't move ownership of counter into multiple threads. This was hard to see earlier because our threads were in a loop, and Rust can't point to different threads and different iterations of the loop. So looking at this error message, it makes sense to me that we attempted to move it in, and of course it's going to happen multiple times because we're in a loop, so it's not going to work. So I guess like to me it makes sense. Let's fix the compiler error with a multiple ownership method we discussed in chapter 15. Multiple ownership with multiple threads. So we're going to use an RC. Nice. In chapter 15, we gave a value multiple owners by using a smart pointer RCT to create a reference counted value. Let's do the same here and see what happens. We'll wrap the mutex t in RCT, enlisting 1614, and clone the RCT before moving ownership to the thread. Now that we've seen the errors, we'll also switch back to using the for loop, and we'll keep the move keyword with closure. So we're going to bring in standard RC. We're going to put the mutex inside of RC. And RC is standing for reference counter here. So now inside of our for loop, we're going to be able to counter equals RC clone. So before we spawn the thread, we're going to clone the counter, which is the mutex. Then the counter is going to be able to be used by the thread. Probably because if we didn't do it, we tried to clone inside the thread, that means the RC would be moved inside. But the RC itself can't be cloned. So just this thread in here. So we can't do that easily inside the thread. We have to do it right before. Handles.push handle. And then everything else should be the same. So let's go ahead and do this ourselves. So standard RC. So RC. Okay, so we need to create our counter is going to be an RC new. We're going to put in our mutex. Our containing threads is going to stay the same. We have our for loop here. Now we need to clone this counter. So it's really going to be cloning the mutex counter. So what we really want to do is say like maybe set what do they use as their naming? So counter is this. The counter equals, okay, so I guess because we're in another block right here, we don't care about overriding because we won't need that one. So let counter equals, it's not really shadowing, it's just in another scope. That counter equals, and it's going to be the counter clone. No, it's RC clone counter. So RC. It is clone. I don't know why some of these don't show up in my autocomplete here. That's like a slightly annoying. And then we're going to pass in a reference to counter. Do I have to unwrap that? No, I don't. Okay, so that gives me the counter here, and then we can now use this exactly as exactly as we did previously. And then everything should be fine and dandy. Let's see if this works. The trait bounds standard RC mutex, standard RC sync mutex, standard marker send is not satisfied. Let t thread spawn cannot be standard RC cannot be sent between threads safely. The trait standard marker send is not implemented for standard RC required because it appears within the type. Okay. Required by thread spawn. Okay, so we're probably going to have one more thing to do with this. Once again, we compile and get different errors. This compiler is teaching us a lot. So now it tells us, yep, we can't send between threads. Wow, that error message is very wordy. Here are some important parts to focus on. The first inline error said standard RC, standard sync mutex, cannot be sent between threads safely. The reason for this is in the next important part to focus on, the error message. The distilled error message says the trait bound send is not satisfied. We'll talk about send in the next section. It's one of the traits that ensures the types we use with threads are meant for use in concurrent situations. Unfortunately, RCT is not safe to share across threads. When RCT manages the reference count, it adds to the count for each call to clone and subtracts from the count when each clone is dropped. But it doesn't use any concurrency primitives to make sure that changes to the count can't be interrupted by another thread. This could lead to wrong counts, subtle bugs that could in turn lead to memory leaks or a value being dropped before we're done with it. What we need is a type exactly like RCT, but one that makes changes to the reference count in a thread-safe way. Atomic reference counting with argt. Fortunately, argt is a type like RCT that is thread-safe to use in concurrent situations. The A stands for atomic, meaning it's an atomically reference counted type. Atomics are an additional kind of concurrency primitive that we won't cover in detail here. See the standard library documentation for standard sync atomic for more details. At this point, you just need to know that atomic works like primitive types, but are safe to share across threads. You might then wonder why all primitive types aren't atomic and why standard library types aren't implemented to use argt by default. The reason is that thread safety comes with a performance penalty that you only want to pay when you really need to. You're just performing operations on values within a single thread. Your code can run faster if it doesn't have to enforce the guarantees atomics provide. Let's return to our example. argt and RCT have the same API, so we fix our program by changing the use line, the call to new, and the call to clone. The code listing 1615 will finally compile and run. All right, so let's see if we can do this on our own without looking at the example. So we don't want RC anymore. So is there an arc? So already don't see that, and the autocomplete wasn't helping. So standard sync mutex and arc. Oh, interesting. So it's not here. Okay, so we're going to use standard sync mutex and arc, and now instead of RC, we want to use arc. Cannot borrow immutable local variable C as immutable. Okay, so no more error showing there. It should just work then. The local number is 6. 6, huh? That feels like it wasn't exactly what I wanted. Interesting. Look at that. So I'm getting different numbers here between 0 and 1 because the end thread is ending before this is before it's complete. That's actually really, I wonder if they're going to run into that. Or, you know what? This is where the joins come in. I don't get an error. It just is not going to finish. So we run the join, right? Because join is going to wait for it to finish. It's not like join on a on an array or a vector of some kind. Okay, so for t in counting threads, we want to t.join. like that. And then this should guarantee that our numbers work in the right order. Oh, unused results, so that's why we need to have the unwrap too. And now every single time we're going to get the total number is 10. This code will print the following: result 10. We did it! We counted from 0 to 10, which may not seem very impressive, but it did teach us a lot about mutex T and thread safety. You could also use this program structure to do more complicated operations than just incrementing a counter. Using this strategy, you can divide a calculation into independent parts, split those parts across threads, and then use a mutex T to have each thread update the final result with its part. Similarities between refcell-T, RCT, and mutex/arct. You might have noticed that counter is immutable, but we can get a mutable reference to the value inside it. This means mutex T provides interior mutability, as the cell family does. In the same way we used refcell in chapter 15 to allow us to mutate contents inside an RCT. We use mutex T to mutate contents inside an arct. Another detail to note is that Rust can't protect you from all kinds of logic errors when you use mutex T. Recall in chapter 15 that using RCT came with the risk of creating a reference cycles, where two RCT values refer to each other, causing memory leaks. Similarly, mutex T comes with the risk of creating deadlocks. These occur when an operation needs to lock two resources, and two threads have each acquired one of the locks, causing them to wait for each other forever. If you're interested in deadlocks, try creating a Rust program that has a deadlock. Then research deadlock mitigation strategies for mutexes in any language and have a go at implementing them in Rust. The standard library API documentation for mutex T and mutex guard offers useful information. We'll round out this chapter by talking about the send and sync traits and how we can use them with custom types. Extensible concurrency with the sync and send traits. Interestingly, the Rust language has very few concurrency features. Almost every concurrency feature we've talked about so far in this chapter has been part of the standard library, not the language. Your options for handling concurrency are not limited to the language or the standard library. You can write your own concurrency features or use those written by others. However, two concurrency concepts are embedded in the language: the standard marker traits, sync and send. Allowing transference of ownership between threads with send. The send marker trait indicates that ownership of the type implementing send can be transferred between threads. Almost every Rust type is send, but there are some exceptions, including RCT. This cannot be send because if you cloned an RCT value and tried to transfer ownership of the clone to another thread, both threads might update the reference count at the same time. For this reason, RCT is implemented for use in single-threaded situations where you don't want to pay the thread-safe performance penalty. Therefore, Rust type system and trait bounds ensure that you can never accidentally send an RCT value across threads unsafely. When we tried to do this in listing 1614, we got the error, the trait send is not implemented for RC mutex I32. When we switched to arct, which is send, the code compiled. Any type composed entirely of send types is automatically marked as send as well. Almost all primitive types are send, aside from raw pointers, which we'll discuss in chapter 19. All right, so before moving on to the rest, I guess like we're so close. I'm going to go ahead and finish up, and then we'll be ready to move on to chapter 17 tomorrow. Allowing access for multiple threads with sync. The sync marker trait indicates that it is safe for the type implementing sync to be referenced from multiple threads. In other words, any type T is sync if $T, a reference to T, is send, meaning the reference can be sent safely to another thread. Similar to send, primitive types are sync, and types composed entirely of types that are sync are also sync. So like a vector, right? The smart pointer, RCT, is also not sync, for the same reason that it's not send. The ref cell T type, which we talked about in chapter 15, and the family of related cell T types are not sync. The implementation of borrow checking that ref cell T does at runtime is not thread safe. Smart pointer mutex T is sync and can be used to share across multiple threads, as you saw in the sharing in mutex T between multiple threads section. Implementing send and sync manually is unsafe. Because types that are made up of send and sync traits are automatically also send and sync, we don't have to implement those traits manually. As marker traits, they don't even have the methods to implement. They're just useful for enforcing invariants related to concurrency. Manually implementing these traits involves implementing unsafe Rust code. We'll talk about using unsafe Rust code in chapter 19. For now, the important information is that building new concurrent types not made up of send and sync parts requires careful thought to uphold the safety guarantees. The Rustonomicon has more information about these guarantees and how to uphold them. Summary. This isn't the last you'll see of concurrency in this book. The project in chapter 20 will use the concepts of this chapter in a more realistic situation than the smaller examples discussed here. As mentioned earlier, because very little of how Rust handles concurrency is part of the language, many concurrency solutions are implemented as crates. These evolve more quickly than the standard library, so be sure to search online for the current state-of-the-art crates to use in multi-threaded situations. The Rust standard library provides channels for message passing and smart pointer types, such as Mutext and ArcT, that are safe to use in concurrent contexts. The type system and the borrow checker ensure that the code using these solutions won't end up with data races or invalid references. Once you get your code to compile, you can rest assured that it will happily run on multiple threads without the kinds of hard to track down bugs common in other languages. Concurrent programming is no longer a concept to be afraid of. Go forth and make your programs concurrent, fearlessly. Next, we'll talk about idiomatic ways to program models and structure solutions as your Rust programs get bigger. In addition, we'll discuss how Rust idioms relate to those you might be familiar with from object-oriented programming. All right, and so that is going to be the end of chapter 16, which means we're ready to sort of fix this up. Which one is this? I'll just add them all. Okay, so this is going to be threads with messaging and shared memory. Want to close you and head back to the root of the project so we can update the README with where we're at. Okay, so currently at, now it's going to be object-oriented programming features of Rust. And our URL changes. Much simpler for this one, but we'll see how long chapter 17 is. It's going to be interesting. OOP. I began with OOP when I first started learning more complex programming, and then more recently have been switching to more and more functional style programming. Okay, so I've got all of this. Let's go ahead and update. Now on to chapter 17. And we'll go ahead and send up the code. Okay, I did an update, and now can I do a git push? Okay. Then I'm able to push that up. So if we come up to the Learning Rust, this repo, which I do have linked in the stream description, that is now where we're at. So you can go to that section of the book, and also all of the code that we've been working on, specifically like chapter 16 and the concurrency, is here as well. I'm doing all of these streams every weekday morning at 7 a.m. Mountain Time before I head off to work, and today is no exception. I'm gonna have to go get ready, then head to work. Hopefully it's not gonna rain on me while I commute, but other than that, it sounds like it's gonna be a normal, pleasant day. Perhaps not like as hot as it's been recently in Denver. If you want to get notifications when I'm going live, I'm tweeting out, but I'm sort of tweeting at the moment to go live. That kind of relies upon me to remember that I'm doing that. If you don't want to rely upon my memory, then go ahead and follow me on Twitch here. I'm also archiving these videos to YouTube, and you can follow me there to get notifications of those videos as well. With that, I'm going to go get ready for the day. So thank you everybody for stopping by, and I'll see you tomorrow morning.